The action potential. How do we know what a nerve impulse is and how it is created? Scientists studied the giant squid axon. They placed electrodes inside the nerves of the squid. They found that resting membrane potential inside the axon is negative 70 millivolt. This is when the neuron is not active. An unstimulated axon is negative on the inside in respect to the outside. During an action potential, the neuron becomes positive on the inside, positive 40 millivolts. This is when the axon becomes excited. Every time the axon is stimulated, there's a change in charge across the membrane. It is not the entire neuron that is stimulated at the same time, however, it's just one portion of it. So there's the action potential where it is positive 40 millivolts on the inside. This wave of depolarization travels down the axon until it reaches the end and is carried to another neuron or an effector. Phrases to describe the action potential include moving wave of depolarization, propagation of the action potential, an electrical signal is traveling down the neuron. So resting neuron is negative 70 millivolts on the inside. The charge difference is due mostly to positive ions. There are more sodium ions outside the neuron than potassium ions inside the neuron. This separation of charge gives the neuron polarization. So it's positive on the outside and negative on the inside at rest. So we see outside the neuron, we have high sodium and low potassium. On the inside, there's high potassium and low sodium. And overall, there is less potassium than there is sodium. When an action potential hits, the first step that happens is sodium diffuses into the neuron. Immediately following that, potassium diffuses out of the neuron. Then to get the neuron to be polarized once more, the sodium-potassium pump works and pumps 3 sodiums out for every 2 potassium in, and this requires ATP. The sodium-potassium pump actively takes 3 sodiums out and brings 2 potassium in by using ATP to maintain the original concentrations of more positive charges on the outside than on the inside of the neuron. In other words, voltage is negative 70 millivolts inside the axon. So the sodium-potassium pump takes 3 sodiums out and it requires a molecule of ATP. The splitting of ATP provides the energy to change the shape of the channel. The sodium ions are driven through the channel. Sodium ions are released to the outside of the membrane, and the new shape of the channel allows potassium to bind. Release of the phosphate allows the channel to revert to its original form, releasing the potassium ions on the inside of the membrane. When a neuron is excited, an action potential is generated. The sodium-potassium pump is turned off during an action potential. Let's label the parts of an action potential. When there is no stimulation, we say the action or the neuron has resting potential or is polarized. At the top, it has action potential or it is depolarized. Dipping below the line is called hyperpolarized. And back to resting potential, we say the neuron is repolarized. So the ions that are causing this to happen, first of all, the depolarization is caused by sodium rushing into the neuron. The repolarization starts with potassium rushing out, and then the sodium-potassium pump moves 3 sodiums out and 2 potassiums in until it has reached resting potential again. Let's also label threshold. Threshold is the minimum amount of stimulation required to cause an action potential, and on this neuron, it is negative 55 millivolts. The time that it takes a neuron to recover before another action potential can occur is called the refractory period. Let's talk about the toilet flush analogy. Depolarization is like flushing a toilet. So the toilet is empty. The tank is empty and cannot be flushed again until the tank refills. So as it's refilling, it is repolarizing. The time that it takes to refill is the refractory period, during which you cannot flush the toilet again because the tank is not full yet. Threshold level is the minimum level of stimulus required to produce a response. It's usually negative 55 millivolts. These two stimuli are subthreshold. They weren't high enough to cause depolarization. Toilet flush analogy continued. Threshold is the minimum amount of pressure required to fully depress the handle. If the handle is just tapped, so subthreshold, it will not flush because it did not reach threshold. All or none response. Neurons either reach threshold and fire, or they don't. There's no half firings, there's no slower firings. They are the same every time. And by same, we mean the intensity and the speed. So it depolarizes to the same intensity and takes the same amount of time for each depolarization. Toilet flush analogy continued. The all or none response means that every time the toilet is flushed, the same amount of water is used, and it takes the same amount of time to refill the tank. So how does your brain know when a stimulus is greater? If all neurons fire to the same intensity and speed, then how does your brain know that you are holding a hot cup of coffee versus accidentally touching a hot burner? If there is a greater stimulus, then firing frequency will increase and the number of neurons recruited will also increase. For more information on this, take a look at the Nervous System Crash Course. So here we see greater stimulus. This is higher frequency. So here's low frequency and here's higher frequency. So higher frequency is the result of a greater stimulus. The neuron would fire more often. Also, lower stimulus means fewer neurons are recruited. Higher stimulus means more neurons are recruited. Let's take a look at the axon again, noting we know that this is depolarized because it's positive on the inside. So let's start there. The direction of nerve impulse is this way. Let's take a look at this neuron, and we can see the nerve impulse is traveling down the axon. Right now it's polarized. This is the point of depolarization, and right behind it, it is repolarized. So number 1 is behind the moving wave of depolarization at number 2, so it is repolarized. And 3 is in front of it. The moving wave has not hit it yet, so it is still polarized. For another good explanation of this concept, take a look at this neural impulse video. Okay, so once more, as the moving wave of depolarization travels down the axon, here we have depolarized moving down the axon. In front of it, it is still polarized. Behind it, it is repolarized. And then once it is repolarized, back to resting, it is now polarized again. Inhibitory drugs will lower resting potential, making it harder to generate an action potential. Alcohol affects acetylcholine in the brain. So brain on alcohol, we see that alcohol lowers the resting potential, making it less likely that the neuron will fire. Instead of just a 15 millivolt stimulus to reach threshold, it would require a greater stimulus. A stimulus will not cause the neuron to reach threshold until it is at least 35 millivolts for the brain on alcohol. The person would not respond to subthreshold stimuli. For example, they may not feel pain. Action potentials in a myelinated versus an unmyelinated neuron. So in the myelinated neuron, the action potentials only happen at the nodes of Ranvier through saltatory conduction. And remember that at the nodes, it helps to propagate the action potential. In an unmyelinated neuron, the action potentials occur along the entire length of the neuron, which means there is slower transmission.